Hi everybody, this is the second video of thermodynamics. In this video, I'll be talking about the second law of standard thermodynamics and Gibbs free energy. So before that, we'll touch on the first law of thermodynamics. In this, we know the change in internal energy is equal to the change in heat plus work. Okay. We talked about that if the work is done on the system, it is positive. If it is work is done by the system, it is negative. So in chemistry, we write it like that, considering the work is done on the system. But if it is physics, work done by the system, so we put a negative here instead of the positive. Okay, so all right. So the work here, so this D means consider delta as the big change and small d as the smaller change. So we know dq and dw are, or q and w, both are path functions. U is a state function depending on from one state to the other. So work, if it is just PD, pressure and if we consider work is only involving pressure and volume, so work is given as PdV and PdV work. But if it is done under constant pressure, which most thermodynamics work is, because it's in the lab, so atmospheric pressure is 1 and it's a constant, we can just take this equation. And so now, this is just refreshing what you know. Now here, you can see this pressure here. Now, if you go to the gas laws, you may remember that PV equals nRT, because we are telling here that only the gas pressure PV work is considered here. So we can use this one. So imagine the gas is expanding, then the system is pushing, so against the system is working against the surroundings, so the work is done by the system. Okay, so that's put a negative there. So this pressure, if you take, I'll write it somewhere here, if you take it as replace this P here. You don't have to know to derive. All I want, remember these important equations where when I notify these ones like that. Okay, so then here it will be, remember this W negative sign is because depending on the work. Okay, so if I just take it here, so first putting N. Then from this we get a equation where we say W equals, or the work equals nRT. Okay. So whether you get a positive or a negative value depends on which way the work is going. So remember these two. Okay. So then we talked about second law, which talks about, so this is something you should remember. Remember that this disappears because it has constant pressure. So those are the conditions you must remember. So then only you can apply those equations correctly, because we are not going to do a lot of derivations. We're not going to do derivation because this is for general chemistry. So at this level, knowing this information is sufficient. Now we say the entropy S, the change in entropy is always increasing in a system, and that so the total the universe, so the system surroundings here is coming from the previous one. So this is the universe. Together we say the universe. Okay. So delta S of universe is equal to the delta S of system, delta S of surroundings. Okay. Now, in a reversible reaction, we studied this bit too. Delta S equal to Q, remember it's reversible, over T. Okay. So then there'll be the Q reversible for the system and Q reversible for the surroundings. Okay. So if I for the universe, it will be Q for the system, they are reversible, plus Q reversible together. Okay. And from the previous one, we learned that, so these are the ones you remember. This one, which we did last time. Perhaps this, just the knowledge of this universe is a combination of systems and surroundings. Then Q reversible, because we are using Q reversible here, you know, nRT ln. Okay. So always, if Q reversible in system is positive, the surrounding should be negative. If surrounding should be positive, the other one, because it's the exchange between the surroundings, the heat system, right? So it goes this way and the other way. So if Q for the system is negative, just you can put whatever way consider. So if it then if it is the Q system is positive, then it should equal to Q surroundings. Doesn't matter. So for the Q surround is negative. If it is the other way, positive. So that is how the entropy is expressed, but and that is also how the entropy is explained. Okay. Now there were certain names you need to know that try to explain the entropy, that we know that entropy increases and how the heat flows from one system to the other system, or one engine to the other, or the surroundings. Okay, so one was Carnot. We will do Carnot engine and measuring efficiency in another video. So Carnot is also known as father of thermodynamics. So he has a Carnot engine that gives the maximum efficiency engine. So he explained the second law of thermodynamics with different concept, and he uses the Carnot engine to explain that the heat cannot flow from one state to the other completely without using some for work. Okay, so we lose. And the other person is Clausius. He said heat generally cannot flow spontaneously from a lower to higher. Spontaneously it goes from higher to lower. Okay, because it's a diffusion. But if it is lower and to higher, then you need to do work. So Clausius said that it cannot go from lower temperature to higher temperature. Heat cannot flow naturally, spontaneously. A spontaneous reaction, entropy works in a way to increase. Now, then Lord Kelvin, who was William Thomson, later known as Lord Kelvin, because we use Kelvin, he said, in a cyclic process, so if I have those two, you cannot completely put Q1 and the entire Q1 here. It is always Q1 is going to be more than Q2, because when it is going from here to here, it loses energy. Some of the energy is lost. So that's what he explained. So these things combined, what it says is when you're converting heat from one point, when you're taking heat from one point to the other, you need to do work. So the heat that is flowing from state 1, 2, some of that is lost for work to make it happen. Okay. Let me talk about another term here called Gibbs free energy. Term, then I will explain something you need to know when you're applying this knowledge. So the application of this knowledge, you'll have to watch a video on how I'm going to be solving questions. Okay. Gibbs free energy. Now, Gibbs free energy equation is delta G equals delta H minus delta S. Okay. So these terms you know, T is the temperature, S is the entropy change, and H is the enthalpy. Enthalpy you have done previously. Okay. Now look at these conditions, how delta G value would have, whether it will get a positive or negative value. Now these questions, these general questions you get in an exam. So for a reaction to happen, the net reaction should give a negative value. So if the delta G value, what is delta G means? Delta G final minus delta G initial, always, okay? It's for the enthalpy, it's for the entropy, it is always like that. And also, when it comes to the enthalpy, entropy, Gibbs free energy, and there's another one I'm bringing, it's Helmholtz energy, which we put A here, but in physics you might use F, but because it's chemistry you use A. Okay, all these, the standard condition is 180. Okay, and 25 degrees centigrade or 298 Kelvin. This is more or less we carry out all our experiments. These are not hypothetical, these are real experiments we carry out. So at atmospheric pressure and temperature is at 25 degrees roughly, okay, because that's the room temperature. This is considered the room temperature. That's okay. So when we calculated Hess's law, you can understand what we did was, if we are moving from state 1 to state 2, whether we take root 1 or root 2 or 3, it doesn't matter, because all these four I have mentioned here are state functions. Okay. So what matters is the final state minus initial. So it could be for Gibbs, or if it is entropy, that, okay, always. So if you have a reaction, then you get the product entropy value, adding all together, and then deduct it from the initial value. That's the change. That's how you get the change. Okay, always. So delta G to be negative, because that's when the reaction is feasible. gives negative, then we know reaction happens. Okay. So delta G is gives free energy. It says the system's free energy, change of system's free energy when a reaction is taking place. So the amount of energy available for a reaction to take place. Okay, and this delta G is used at constant temperature. Okay, so let us see how we can get delta G H. So what points we can get negative values delta G. So if H is negative, now we know the enthalpy, right? There it could have negative, that is exothermic, positive, that is endo. Then normally delta S happen in a way to increase the entropy. Right? So you can see if I have a positive here and a negative here, value I get is depending on if I have a larger positive and a smaller negative, my value is going to be positive. Right? If it is delta H is an exo situation and this entire thing is also negative, then my delta G value is going to be negative. So that sort of an understanding is necessary when you are applying this equation and the values to a system to find out whether it is spontaneous or not. So I'll just explain different situations, but these are, you should be able to understand this intuitively. Let us see temperature. Delta H, delta S, and delta G. Because if it is negative, it is always spontaneous. Okay. So let us see. So if the temperature is very high, so what I mean is this value here is high. Let me use different color. This T value is high, so high temperature. And if I have delta is negative and spontaneously happen positive, the change in entropy has to be positive for a spontaneous reaction. So it's positive, then delta G is going to be a negative value, right? You can say when delta H is negative, T's value is high and it's a negative, delta is always positive, because if it was a negative, that becomes positive. So that's right. Then this is a spontaneous. Okay. Now, if you have a low temperature, which means this temperature is going to be low. Okay. But still, delta H is negative, delta H is positive, then this is a negative. You can say it is spontaneous. Okay. Let us say scenario some. The temperature is high and delta H is negative, and then delta S is negative. If this part becomes negative, okay, and temperature value is high, so the entire thing is high. This is negative, so this delta S would contribute a larger positive value, thereby taking the negative off. And also, if delta S is negative, it's not spontaneous, right? So delta G is going to be positive. Here, the value, this is going to be non-spontaneous. Okay. You can just understand it, then you will remember it. Different situations, high, low, high, low. So if the temperature is low and the delta H is negative, so these are all exothermic situations. Delta H is negative. And we'll say delta H is negative here too. And then because T is low, although this spontaneous reaction, this is negative, this T is low, so this entire T value would be a small one. Okay, but it's a positive small. Then the negative is high. This is a small relative to the negative delta H value. So delta G is going to be negative. So it's going to be small. Okay. Now go for again high, low, high, low. So delta H is positive. Okay. Now if delta H is positive and delta S is positive, but because delta T is high, write it here instead of moving. So delta T equals H minus T delta S. So if this T value is high, delta S is positive. This is going to be a higher negative. Okay, although this delta H is going to be positive, meaning endothermic, it's still going, delta G is going to be a negative, so this is going to be small. Okay, now what about low? When this entire thing is low, but this is a positive value, it's more likely it is going to be non-spontaneous. Delta G has to be negative for it, but spontaneous, feasible reaction. So high temperature, the last one, sorry, last two, then delta H is positive. This value is positive and delta is negative. Negative, negative becomes positive. So that at the end, what you're getting is not spontaneous. Similar to that, because if it is positive and delta is negative, 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 positive, delta G value is going to be a positive value. So it is not. Try to understand what's happening here. This sort of question is going to help you understand. To answer a question like this, you need to understand the fundamentally what is happening and understand this equation. Okay. Do a small question with say simple reaction where water is formed. Okay. We are given certain values. They're asking what is delta G. Okay. They will say calculate the standard delta G. Standard means 1 atm and 25 degrees centigrade. Okay. So we have to calculate delta G. So what you do, you write the equation first. We have given delta H. Let's say we are given delta H. Simple. It's going to be round figures, but I'll say 250 kilojoules. Another thing to remember is whether it's in kilo or joules, because sometimes they will say whether you're paying attention. Here they will give kilojoules, and somewhere else they will just give joules. Okay? So let's create a situation like that. So, and then delta S is given. Delta S units what? Because S is given by Q over T. That's Kelvin, and that's in joules, right? Energy. So delta S value will say minus, okay, 230. Temperature, say 25. This is standard. Now, all you have to do is just put the values there, knowing that this is kilojoules, okay? So, minus 250 minus is T delta S. So 25 means you have to convert it to Kelvin to 98 times minus 230. Okay. So because it's minus here, minus, I get a positive value there. So it will be delta G minus plus. Now this 230 is joules per Kelvin. Okay. Now remember joules per Kelvin. So if it is, if you're going to get it to kilojoules, you multiply it by 10 to the power 3. Okay. So you know the reason, because positive that. So I just have to multiply those two, 298 times 30. Okay. So 298 times 230, I get 68. Still, we are looking for standard condition. So here minus 250. Then when you have negative 3, this becomes 16.54. Positive, right? So I have to put here positive. Still positive, right? So then my answer is going to be 250 minus 250, 68.54, right? So 68. So I get about 1.6 kilojoules, because now we have converted all delta into kilojoules. So once again, this is a negative, but negative multiplying, you get a negative value. So then positive, then from, so it's reduced, but it is still spontaneous. It's a reduced value, but it's still spontaneous. Okay. Okay. So then that's how you apply delta G. Okay. So now I need to tell you. So when it comes to entropy also, you will have standard conditions. Standard entropy would be at 298 Kelvin and 180. Now, this entropy value, it becomes 0 when it is pure crystalline solids. That means when this the standard of the material is in pure crystal form, which is in one of the natural forms, then that value is 0. Pure. Other than that, you will be given a chart, or the value should be given. Then that's otherwise the in a crystalline form, delta S becomes 0 when at absolute temperature 0 Kelvin. When it is in pure crystal form, means the crystalline substance is 0 at absolute temperature, right? Because pure crystal form, it is perfectly orderly. So if I take structure, So when it takes to the pure crystalline form, it's like that. But above 0 Kelvin, they vibrate. They all vibrate. But when it comes 0 Kelvin, they don't vibrate. They don't move. They are in the perfect form. Okay. So they are balanced nicely. The energy is lowest. So delta is the entropy is 0. That's the point that entropy comes in. So the perfectly ordered crystal form, perfectly ordered crystal form, no, they are just the crystal form of that material, only just one material, and then they become 0. So that is that status, what is expressed in the third law of thermodynamics. So we know the second law, we said that for a reversible process equals, otherwise spontaneous is more than 0 or more than, okay, but when it becomes 0, then it is perfectly when they are perfectly ordered crystal in its pure form, when they're in perfectly ordered crystal, and at 0 Kelvin, the entropy is 0. That's called third law of thermodynamics. Now we know 3 laws. Right? Now the other one is Helmholtz equation, which is A, same as G. Here A is given in terms of internal energy, delta U, T delta S. In this one you have delta H. So here in application is in constant temperature and volume. Here it is constant temperature and pressure. So this is Helmholtz. Okay. Now derivations have a relationship. It's called Maxwell relationship. Okay. Now I'm just going to note them. You don't have to derive them. How they are related. Okay. So if I take U, which is internal energy, these are derived through partial differentiation. So you don't have to derive them. But these are derived through partial differentiation. Okay. So here U is expressed in the variables of entropy and volume. Entropy and volume. Okay. So if you just say internal energy is a function of entropy and volume, and then you go on to is the function of that. So then you get a series of that. So for internal energy, you have this differential equation. You have to remember equals T. Okay. For enthalpy, to then when it comes to Helmholtz equation, as I said, it could be F in some books, but in chemistry we'll use it like that. For partial differentiations, okay? It's derived from that. There are steps before that, but this is the final step. So remember these ones. And then for Gibbs free energy finally. Okay, so here internal energies, the variables here are entropy and volume, and here entropy and pressure, volume and temperature, and pressure. Right. So these could be used and applied depending on the situation. When we do, you may not be applying at this stage these very much, but I want you to have it here that they were derived from previous calculations. Okay, now I have given all that. I can't remember it. So, having said all that, I hope you can remember this enthalpy. We have two states, and enthalpy values are there. Similar to that, you will have different entropy values, G values, and depending on the situation. Okay, and if you apply these equations you have learned here, you have to see the conditions, and depending on those conditions, you would be applying them. Okay, so example, if I want just to show you how we derive this dH, TdS, VdP, you don't have to know how to derive it. Okay, but normally enthalpy is defined as U plus PV work, pressure and volume, PV work. Okay, so if I write this as the change in enthalpy, change in internal energy plus the change in pressure and volume. So we do partial differentiation, so we can say PdV. Just trying to show you how it's applied, right? So, and then here we learned du plus TdS PdV. Right? So if I put that here, so then I get V. Right, where's VdP here? DH equals TdS plus VdP. So I got this equation. So that's how you, by combining, you can get these values. Okay. So you know there are several equations. The ones you have to remember have across. So this lecture is not just you watch the video, but you have the notes you're looking at, and then you can remember these equations, which I'm telling you, write them down. Then you, when you get a question to solve, you look at it and say which one, which equation should I use? Okay. Just trying to see. Also, please review how you calculated enthalpy, the difference on enthalpy by the products minus delta H. How delta H also was 0 points. Now, third law says entropy is 0 for any element if it is in the pure perfect crystalline form at 0 Kelvin. So, can you remember we said delta H is also 0 if they are at 1 atm and 290 K, if they're in the element form, like if you get oxygen gas, it would be 0. Standard would be 0. nitrogen just in the form. Similar to that, only entropy works. Just because there's a new word, entropy, that is referring to disorder. Don't be alarmed. Just use these equations. You will see how we use these equations when I do some questions and answers. All right, thank you.